Okay, great. Last but not least, we have Hayam talking about secure range searching using Copy-And-Recurse. The floor is yours.
Thank you for the introduction, Stephanie. So I was told that you are more likely to remember the last talk of a conference, so I hope to leave you with good memories of PETS 2024. So this is a work together with Eyal Kushnir and Guy Moskovich. We are from IBM Research. The motivation for our work is databases that are encrypted with FHE, fully homomorphic encryption, usually stored on the cloud, and that we want to query with queries such as what is the average sugar level of a patient whose age is between 30 and 40, and LDL level is between 130 and 160. So it should be mentioned that we are interested in non-interactive protocols, so that's only one round. So solutions such as ORAM and other MPC techniques are not applicable. So we have to go with FHE, fully homomorphic encryption. And it is also worth mentioning that there are already companies that provide analytics as a service with FHE on the cloud. So it makes sense to try to improve these services. So we think of our database, or the records in our database, as points in some higher dimensional space. In this case, it's going to be a two-dimensional space where the x-axis is the age and the y-axis is the LDL level. And the query that we see here is actually a rectangular region, and we want to query something on the points inside this region. So our solution is not restricted to rectangles. It can also be more general ranges and higher dimensions. But in this talk, for simplicity, I'm going to assume the database is only one-dimensional. That means points are actually one value. And the ranges are going to be a segment, all the points between A and B. And the goal for this talk is going to be just to count how many points are inside the ranges, inside the range, the query range. See the paper for details for higher dimensions and more generic ranges and more complicated functions. This talk is going to be simple, I hope. So what would the plaintext algorithm do? Let's start with something simple. So assume you have a database with P being 1, 2, 4, 4, 5, 7, 7, 8, 8. The plaintext algorithm will partition these points into groups and try to make something of each group by itself. So a partitioning could be like 1, 2, 4, 4, 5, 7, 7, 8, 8. And we can also store with each group a bounding segment that is the smallest point and the biggest point. So I'm going to use interchangeably the point with value because higher dimensions is point, but for one dimension, a point is a value. So each group is going to keep a bounding segment, which is the smallest point and the biggest point of each group. And if we have a query range such as all the points between 5 and 8, then we can quickly see with little checking that the bounding segment is disjoint from the query range. And so we can know that we can skip all the points in this group. We can just ignore it. Similarly, we can see that the bounding segment of the third group, 7, 8, is totally contained inside the query range, so we can just count all the points inside this group without any further checks. The middle group is more complicated, so the bounding segment crosses the query range, so we cannot say anything intelligent about the points inside this group, and we have to look into further partitioning of this group and continuing recursing with this group. So this suggests a tree-like data structure, which is called in the literature partition tree. So in this example, this is a ternary tree. Every node has 3 children, but 3 is just a parameter, R, but that can be of a different value. So the leaves of the tree are going to be associated with elements of the database, and inner nodes of the tree are going to be associated with subsets of the database, which are the values in the leaves of the subtrees that they have. And also each node is going to keep the bounding simplex that bounds the points inside that it represents. And for one dimension, we can also say that at each node, the query range is going to cross at most 2 children, the bounding segment of 2 children, which is also a guarantee that we will need to recurse in plain text. We are going to need to recurse into at most 2 children. So generalizing this to higher dimensions is very complicated, details in the paper. So what are the challenges of FHE, fully homomorphic encryption? So with FHE, we cannot skip a group. We cannot ignore a group because FHE works in circuit model. We need to apply the same set of operations for every input. So we cannot just ignore a subset. And as was already noted earlier in this conference, in one of the earlier days, we need to do something with every node of the tree, but this thing can be very simple, like a multiplication or maybe 2 multiplications. And we should strive to try to minimize the number of comparisons that we make. And actually, comparison is what takes most of the time for the algorithm, both the plain text and under FHE. So it makes sense to try to try to minimize the number of comparisons. So let's denote by T the time to make a comparison between a query range and a bounding segment or a point. And we want to express the time complexity with T also and not only with N. So the plaintext algorithm would take T times log N. There's a lower bound for FHE of order of N. The naive algorithm under FHE will just check every point whether it is contained inside the range or not. So that would take O of T times N. And our algorithm will take order of T times log N plus N, which seems to be the best we can hope for. We are going to do that with a technique called Copy-And-Recurse, which is what I'm going to describe next. So if there is one thing that you're going to take from this talk, I mean, I hope you're going to remember everything from this talk, but if you're going to take one thing from this talk, let it be Copy-And-Recurse. So what is Copy-And-Recurse? So Copy-And-Recurse is a technique to efficiently traverse a tree under FHE. So we are focused on FHE, but this is like more general and can be applied to other MPC techniques. So using Copy-And-Recurse, traversing a tree takes the similar time complexity to the plain text algorithm, but we are going to pay a linear overhead. So Copy-And-Recurse needs 2 prerequisites. The tree needs to be full, and we also need to have an upper bound of the number of children that we need to recurse into at each node. So let's see how Copy-And-Recurse works. So we started the root. The root, in this case, has 3 children. We compute for each child whether we need to recurse into or not. So this is done under FHE. So under FHE, we're not going to get a result, a plain text result that we can make a decision on, but we're going to get a ciphertext that is going to encode a 0 if we don't need to recurse into that child, or 1 if we do. And remember that we have a bound, that there are at most 2 children that we need to recurse into. So this example, by the way, does not comply with the previous example. So here we're going to recurse into the middle child and the right child. So after having figured which children we need to recurse into, we're going to use a selection matrix. So a selection matrix, you can think of it as a generalization of a MUX, a multiplexer. So a multiplexer gets 2 inputs, and using a condition bit, it selects which of the inputs is copied to the output. Selection matrix is a generalization of that. It gets R inputs, and using the indicator vector, it copies some of those R children to the output. So after having copied the children that we need to recurse into, we recurse into them. And the nice thing about it is multiplying by the selection matrix yields linear overhead, but after we have done so, continuing in recursion into the children takes the same time as the plain text algorithm. So the time bounds for our solution, well, I'm not going to read it. You can read it by yourself later or now or sometime later. We implemented our algorithm, and the experiments show match what we expected in theory. So you can see here the blue line is the naive algorithm. The other lines is our algorithm with different parameters of R. So you can see that everything in asymptotically everything is linear, but our slope is smaller than the naive slope. We also pay some overhead that is more significant when n is small. We also implemented it in 2 dimensions when the ranges are axis parallel rectangles. Again, things are more or less linear, and there's some overhead that we need to pay. Again, this is what we expect from the theory. So now to recap, so we showed Copy-And-Recurse, which is a technique. We focused on FHE, but it's not only for FHE, for any arithmetic circuit, actually. Copy-And-Recurse, a technique to traverse a tree efficiently. With it, we showed how to traverse partition trees, and we used partition trees to show how to answer range queries, range searching queries. So I think I have 30 more seconds. So I prepared a haiku version of this talk that you can enjoy on your way back on the train, unless you live here, and then you don't. You'll have to enjoy it somewhere else.
Thank you for the talk. Questions up there?
Thanks. Really interesting talk. I have a couple of questions. So how do you decide if you recurse or not? You mentioned this is done under FHC. Is it like some kind of comparison?
Yes. So you need to implement comparison under FHC. So this is okay. So let's stick with the one-dimensional case. So this has to do a lot with the scheme that you're using. So if it's CKKS or not. So let's we implemented it under CKKS. So under CKKS, so basically you have two segments, like the query segment and the bounding segment. So you actually need to find whether one endpoint is between the other 2 endpoints. So that's 2 comparisons. So basically comparison with CKKS is done by taking, by checking the sign of the difference. For the sign function, there are a lot of work of how to compute the sign function. So just take 2 differences and see if the signs are different. If they are different, then, well, you're in this position, this position. Yeah, so I hope that answered the question.
Yeah, it does. Are you taking advantage of batching in any way? And you
of what?
Of batching, like packing capabilities of CKKS?
Yes, so our technique is indifferent to packing. So it works with TFHE, for example, with no packing in TFHE. With packing, well, obviously the easiest way is to just perform the query over 60,000 databases in parallel.
The reason I'm asking, and sorry to interrupt, is that in one slot of the packed message you might need to recurse, and in the other you might not need to recurse. So I wasn't sure how this actually gets resolved. Mm-hmm. And if you're not using packing, why not TFHC? Wouldn't it be more efficient?
So our solution is indifferent to the scheme. So yeah, it can work with TFHE as well. We were more interested in CKKS because, well, it was our motivation came from CKKS actually. So that's why we were interested in CKKS, and we actually used to search many databases in parallel. So we took the easy way out.
Makes sense. Thanks. Very interesting work.
Thank you.
I think someone else was first. So maybe you did this in the paper, but is there some analysis as to what is the optimal choice of R? And one reason why I'm also asking is for another paper that was also tree related, the optimal value for R in that case turned out to be E. So I'm wondering, maybe there is some some version of the algorithm where if you sometimes switch between, let's say, 2 and 3 or 3 and 4, that you might get a better result than just fixing R?
Yeah, so that's an excellent question, by the way. Yeah, so you can see that for different choices of R, you do get different times. Yeah, so we didn't actually think of how to choose R more intelligently than just checking all the R's.
Thank you. But it's a very exciting algorithm. Thanks.
Thank you.
Okay, I think we had one more question here.
So I suppose the sign function you were talking about is like if A is less than B, then sign is 0. If they are equal, it's half. And if A is greater than B, it's 1, right?
Yeah.
Okay. So how do you approximate that function? You mentioned like you are using CKKS, and hence I guess.
Oh, so there are
Yeah,
a lot of work in that area. So we didn't. I mean, we just used what was best of practice. So yeah, I think it's better to take it offline. Like I can give you an intuition, but the details you have to read in the paper.
Thank you very much.
Let's thank the speaker again.